This is section 5.6, Indeterminate Forms and Hopital's rule. We already know that 0 divided by 0 and infinity divided by infinity are called indeterminate. Because we've had limits that if we tried to substitute into them, we would get those answers, and then we had to perhaps do some kind of algebraic trick to proceed with finding the limit. They're indeterminate because we don't even know if there's a limit at all. We don't know what the limit will be before we do that algebraic stuff. So we really don't know much about what our answer will be. So when we've encountered one of these indeterminate forms, we've tried to do like this one, which is in the notes. Something like the limit as x approaches -1 for 2x squared minus 2 divided by x plus 1. And of course, when you substitute, when you substitute in -1 for each x, you get 0 over 0. And so one thing that we talked about doing was factoring and canceling. So let's see if that's going to work on this one. The reason I mentioned that is that there is a common factor of 2. So it at least factors that much. And then that difference of squares factors to be the product of conjugate binomials. So x squared minus 1 factors to be x plus 1 times x minus 1 divided by x plus 1. And the x plus 1 cancels. Leaving 2 times x minus 1. And then once that canceling has occurred, you should try substitution again. And we get an actual numerical answer, -4. And of course, this one was the one that by substitution we started out with 0 divided by 0. And in this particular case, the limit actually does exist, and the limit is -4. But just by substitution and getting 0 over 0, we did not know that would be the outcome. Okay, let's look at another one. This one also should be in your notes. As x approaches infinity, 3x squared minus 1 divided by 2x squared plus 1. And this trick we used here, when we substitute, we're going to get infinity over infinity, which of course is indeterminate. And the trick we use for this one, as x goes to infinity, is to find the highest power of x in the denominator, which is x squared, and multiply by 1 in the form of the reciprocal of that highest power of x over itself. And that's the trick we used. And so, of course, this is all review. This is stuff that we already know how to do. If I distribute the 1 over x squared, I get 3 minus 1 over x squared in the numerator. And then distributing 1 over x squared into the denominator, I get 2 plus 1 over x squared. And of course, the limit of the constant 3 is 3 minus the limit of any constant over a power of x as x goes to infinity will go to 0. Of course, the limit of a constant is that constant. And again, we get 0 there. And this time, the indeterminate form actually did have a limit, but the limit was 3/2. Now, this actually works sometimes, even with transcendental functions. Like if I were asked to do this limit, the limit as x approaches 0 of e to the 2x minus 1 over e to the x minus 1. And that factors. Oh, I'm sorry, let me say first. If you try substitution, e to the 0 is 1, minus 1 is 0. Over e to the 0 minus 1 is also 0. And so that's indeterminate. So we're looking for a factorization. Let me remind you that e to the 2x is the same thing as e to the x quantity squared. And so that numerator factors to be e to the x plus 1 times e to the x minus 1 divided by e to the x minus 1. So factoring and canceling is working yet again. And what you get when you do the canceling after having factored is you get e to the x plus 1. You substitute in the 0 and you get e to the 0 is 1 plus 1 is 2. Now, there are going to be some indeterminate forms where we're going to know an algebraic trick that will allow us to calculate it. It just won't work. And so we're going to have to deal with problems like if there is a transcendental function and an algebraic function involved in the numerator and denominator, it's possible you won't be able to factor, get anything to cancel. So a good example of that would be maybe this one. The limit as x approaches 0 of e to the 2x minus 1 over x. And of course, e to the 0 is 1, 1 minus 1 is 0 over 0. And there's no canceling here because there's no factoring that would lead to a common factor that we could cancel something. If you wanted to, you might think, well, algebraically, can't I split that into two fractions? Let's try that. So that would be e to the 2x over x minus 1 over x. And e to the 2x over x is not going to help us either. Because that leads to infinity minus infinity, which is another indeterminate form. We'll later learn that when we get infinity minus infinity, one thing we'll want to do is sort of the reversal of what we just did, is go ahead and subtract the fractions so that you create a single fraction and then deal with that. So this would actually have been worse to go this direction. We could look at the graph of e to the 2x minus 1 over x and get an idea of what the answer might be. That graph looks like this. No answer there because you can't divide by 0. That graph looks like that. And you could look at that graph and think, well, as we approach 0 from the left side and the right side, looks like we are headed toward a single value, same value from both sides. And we could just look at the graph of that and see, what that is. And it appears to be 2. But it might be 2.000006 or something. So we think it's 2, but it may not be. And that's not very satisfying. We could look at a table of values as x gets closer and closer to 0 to have numerical evidence. And I believe that I put this table in your notes. So as we move towards 0 from the left side, at -1 it's 0.865. And as we move closer, we get 1.8, 1.98, 1.998. And on the other side, when we put in 1, we get 6.389. Put in 0.1, we get 2.214, then 2.02, 2.002. So it does appear to be headed toward 2, but again, we could be fooling ourselves. And so there's really no way to prove it using what you know right now. I'm about to teach you something that a gentleman by the name of Hopital, that he discovered, and this is named for him. Hopital is his name. And the rule says this, that if we get, by substitution, an indeterminate form that's 0 over 0, or infinity over infinity, and by the way, it could be negative infinity over infinity, or one of those infinities could be negative, or they could both be negative, but just most simply, an infinite thing, an unbounded thing over an unbounded thing. If it's one of those, then the limit that we're trying to get, let's say that this is the limit as x approaches a of f of x over g of x. Hopital discovered that in the condition that you substitute and get one of those two forms I've already mentioned, 0 over 0 or infinity over infinity, only those two, that you can get the answer by looking at the limit of the quotient of the derivatives of those two functions. And so what I'm going to say is that whenever we use this rule, I would like for you over the equal sign to tell me that you're changing that thing's form by Hopital's rule by putting over the equal sign capital L, capital H. And that will be your signal to me that you're doing this. So what happens is that by Hopital's rule, we rewrite the limit as x approaches a as the quotient of their derivatives. So the derivative of the numerator divided by the derivative of the denominator. Notice this is not the quotient rule. This is not low d high minus high d low all over the square of low. This is the quotient of their derivatives. And so if we go back to the problem that we just looked at, that was 0 over 0, when we tried to substitute in, so we know we're getting 0 over 0. So that means that it's eligible for Hopital's rule. So by Hopital's rule, this limit as x approaches 0 will now take the quotient of the derivatives of those two functions. So in other words, derivative of the numerator divided by derivative of the denominator. The derivative of e to the 2x, coolest function ever, is itself times the derivative of the inside function. The inside function is the exponential part. The derivative of 2x is 2, minus the derivative of the constant 1 is 0, which I'm not writing, and the derivative of x is 1. And now there is no variable in the denominator, so we should try substitution at this stage, and that should be 2 times e to the 2 times 0, which is 0, which is indeed 2. Just as our numerical and graphical expectation was that it might be 2, we now know that it really is 2. So theorem 5.17 states L'Hopital's rule, and I have a very small version of that here. This is definitely something you need to learn how to deal with, is L'Hopital's rule. And that's going to be a whole lot of what we spend the rest of our time in this recording talking about. So we get lots and lots of practice as we go through some problems. The L'Hopital's rule also works for one-sided limits. So if we were approaching 0 just from the right or just from the left, we can still use L'Hopital's rule if we get an indeterminate form of 0 over 0 or infinity over infinity, if we try that by substitution. So that's also a one-sided limit property that we can use, L'Hopital's rule. Okay, so moving on. You can also use this as x approaches infinity. I have x approaching a. I could just take the a out and put an infinity there, and L'Hopital's rule looks the same. So here a can be, for L'Hopital's rule, a can be a specific number, and it also works if a is representing infinity or negative infinity. So let's do some problems. This is example 2. The limit as x approaches infinity of ln of x over x. So as x goes to infinity, the ln of x heads toward infinity, and x heads toward infinity. And so we have a L'Hopital rule eligible form. So by L'Hopital's rule, this will be the limit as x approaches infinity of the derivative of ln of x is 1 over x. The derivative of x is 1. And when you substitute infinity into the denominator of that fraction, the fraction heads towards 0, and 0 divided by 1 is 0. There are a number of other indeterminate forms that we will encounter besides 0 over 0 and infinity over infinity. Some other indeterminate forms. Let me write this down. Indeterminate. Forms. Of course, 0 over 0, infinity over infinity, and all the variations of that where one or more of those infinities is negative infinity. Both of those are ones where we can use L'Hopital's rule. The rest of them, we cannot use L'Hopital's rule on them in the form that they show up. So here they are. 0 multiplied by infinity is indeterminate. 1 to the infinity. Now, I'm not saying like 1 to the trillion, that's 1. But if you're raising 1 to something that's approaching infinity, that is considered to be an indeterminate form. Infinity to the 0 is indeterminate. Now, if it were 5 to the 0, it would be 1. But infinity is not a constant, so you can't do that. 0 to the 0 is indeterminate. And infinity minus infinity is indeterminate. And so the trick with these other indeterminate forms is rewriting the problem so that it becomes one of the two for which we can use L'Hopital's rule. So they have several examples that you can see there. All of these, if you try substitution, gives you 0 times infinity, or infinity times 0. And looking at the answers, all of those have that form, but the limit for the first one would be 1, the second one is 2, the third one is 0, and the fourth one is infinity. And so you don't know what 0 times infinity will lead you toward. That's why it's indeterminate, and you have to do more to get that answer than just try substitution. That does not work by itself. So as I said earlier, our basic strategy will be to rewrite that indeterminate form, any of those 1, 2, 3, 4, or 5 other forms, into something that would become 0 over 0 or infinity over infinity, so that we can use L'Hopital's rule. Let's do example 4. This is the limit as x approaches infinity of e to the negative x square root of x. Well, if I make the exponent of e go towards the opposite of a huge number, that's headed toward 0. And the square root of an infinitely large thing is headed toward infinity. So that is indeterminate, but we may not yet use L'Hopital's rule. However, because of that negative exponent, you can probably see very easily how this could be rewritten as a fraction by taking that negative power down into the denominator to get rid of the negative. So that's the same thing as square root of x divided by e to the x. And then if we were to try substitution, that's now going to be infinity over infinity. And so it's eligible for L'Hopital's rule. Now keep in mind, radicals are things that we don't leave long as radicals. So I'm going to be thinking in my head that the square root of x is x to the 1/2. So the derivative of that is 1/2 x to the negative 1/2. And then the derivative of the denominator function, coolest function ever, is e to the x. And then algebraically rewriting this in an easier to deal with form, we'll get 1 over 2 e to the x square roots of x. And as x heads toward infinity, the denominator heads toward infinity, and 1 divided by an infinitely large thing is headed toward 0. Okay, so please notice where I wrote the LH, where I wrote the limit as x approaches infinity, and when I stopped writing that limit expression. Those are important. Now, the indeterminate forms up there that look like powers, 1 to the infinity, infinity to 0, and 0 to 0, those are kind of all together in one group, and you treat them in a particular way. So if I were asked to find the limit as x approaches infinity of 1 plus 1 over x to the x. By substitution, 1 over infinity heads towards 0, and 1 plus 0 is headed toward 1. And the exponent headed towards infinity, that's 1 to the infinity. And what we're going to do in the cases where we get one of those 3 forms that are mentioned above, what we're going to do is we're going to set that limit equal to something like y, which creates an equation. And the cool thing about an equation is you can do stuff to both sides of an equation. Before it was just an expression, that limit expression. But saying equals y lets us do stuff. So we're going to do stuff to both sides of this equation and figure out what y is using some algebra and Hopital's rule eventually. Anyway, so what I want you to do with this is do logarithmic differentiation. Take the natural logarithm of both sides. Take me a second to write all this down. Okay. Now, we have a limit property, and it works for infinity as well as for any constant a, that says if we have the limit of a composition of two functions, that's equal to the outer function evaluated at the limit as x approaches a of the inside function. That limit can be taken inside of the outer function part. And because that's true, it's also reversible. So if you notice, the f in this problem, the f is ln of something, and the g of x is this power right there. And so I'm going to use that property of limits in a backwards fashion and take the limit out of the inside of that composition and put the limit out in front. And that will be the limit of the natural logarithm of 1 plus 1 over x raised to the x. Then I can use the property of logarithms that says that the logarithm of a power allows me to take that exponent down in front, and it becomes a multiplier times the natural logarithm of the base of that power. And that's why we took the natural logarithm of both sides. Is by doing this, we were able to bring that variable exponent down into the normal run of things and not have it in the exponent anymore. So if we try substitution on the right, that will be infinity times the natural logarithm of 1 is 0. And so we're doing pretty well. We've changed it from a power 1 to infinity into a product. So we're on the right track. Now, the next thing, and this is what you'll do with indeterminate forms like infinity times 0, that's a product, is that we're going to rewrite that product as a quotient, as a division problem. And we have to choose one of those two to move into the denominator of a fraction. So the easier one is the x. And to put it into the denominator means that we're going to have to take its reciprocal to put it down there. In other words, I'm using the idea that 1 divided by 1 over x is the same thing as 1 times the reciprocal of that denominator fraction, which of course is x. And I'm using that idea backwards here. I have x, and I'm rewriting it as 1 over the fraction 1 over x. Now, when we look at this limit, the natural logarithm of 1 plus 0 heads toward natural log of 1, which is 0. And as x goes to infinity, 1 over x goes towards 0. So this is now eligible for L'Hopital's rule. So by L'Hopital's rule, we'll rewrite that as the limit as x approaches infinity of the derivative of the numerator. The derivative of natural log of something is 1 over that something. Then the chain rule says times the derivative of that something. The derivative of 1 is 0, and the derivative of 1 over x, I'm going to do over here to the side, is the same thing as the derivative of x to the negative 1. And the derivative of that power is the coefficient negative 1 times x to the reduced by 1 power. So times negative x to the negative 2. Divided by the derivative of the denominator, and the derivative of 1 over x is the same as what we just got, negative x to the negative 2. Now algebraically, that negative x to the negative 2 cancels with the 1 in the denominator of the fraction, and the right side argument of the limit simplifies to be simply 1 over 1 plus 1 over x. I have a stray mark there I want to get rid of. There we go. So now, once we've done that simplification, we should always then try to see if it will simplify. I'm sorry, after you've simplified, you should then try substitution again. Said the wrong thing. Sorry. And as x goes to infinity, 1 over x goes to 0, and 1 over 1 plus 0 goes to 1. Now, if you'll remember, our original statement was to find the limit on the right side of that equation, and we temporarily called it y. And the idea was to solve that equation eventually to find out what y is, and whatever y is the answer to our limit question. So using the definition of logarithm, that argument of the logarithm is e to the first, which is, of course, e. And so therefore, the limit that we were trying to find as x approaches infinity of 1 plus 1 over x to the x is e. Okay. So, now I said earlier that L'Hopital's rule can be applied to one-sided limits. I'd like for us to do an example where that's used. So if I had the limit as x approaches 0 from the right of sine of x to the x, by substitution, sine of 0 is 0 to the 0 is an indeterminate form of the type that's a power. So I'm going to call that limit equal to y to get going on this. So I'm going to take the natural logarithm of both sides of that equation. Then I'm going to use the property of limits of compositions to take that limit of the interior function, take the limit part out so that we have the limit of the composition of the natural logarithm of the inside function. Then I'm going to use the property of logarithm of a power to rewrite the natural logarithm of the power as the exponent multiplied by the natural logarithm of the base of that power. As x approaches 0 from the right, we'll get 0 times the natural log of what's getting closer and closer to 0, but from the right side of 0, because 0 is not what we're we can't substitute that in because it can't take the natural logarithm of 0, but the sign of any positive number, that's a number to the right of 0, is positive. And so the natural logarithm of a positive number that's really close to 0 is really far down. It's going toward negative infinity. And so that's a product that is indeterminate. And so that means we're on the right trail here. This looks a whole lot like the last one, as you may notice. So I'm going to rewrite x as 1 over x, and as x approaches 0 from the right, natural logarithm of sine of x still approaches negative infinity, and 1 over positive close to 0 goes toward infinity. Like I said earlier, infinity over infinity, any of those infinities can be negative or positive in any combination. So this is perfectly valid for saying I'm going to use L'Hopital's rule. So because it's infinity over infinity, well, one of them's negative, but that's okay. That means that L'Hopital's rule may be used. So we take the derivative of the numerator function. That's going to be 1 over sine of x times the derivative of sine of x. And the derivative of 1 over x is negative x to the negative 2. Now this time the negative x and negative 2 does not cancel out. So we need to not think that every one of them is exactly the same process. They do get different answers. So don't expect this one to look just like the last one we did. Has some similarities, but it's not the same. So I can rewrite negative x to the negative 2, let me go over to the side, as the opposite of 1 over x squared. And if that negative x to the negative 2 is in the denominator of a fraction, then to do that division, we'll take 1 and multiply it by the reciprocal of negative 1 over x squared, which gives us negative x squared. So this is going to be negative x squared times cotangent of x. Cosine over sine, of course, is cotangent. Now we try substitution, and we hope it works. 0 squared, of course, is headed towards 0. And cotangent of x. Cosine, I could have left it as cosine over sine, because that's probably how I'm going to think this through. Cosine of 0 is 1. And sine of 0 is headed toward 0, but it's positive, so this is headed towards 0 on the positive side. So I'm putting a little plus sign here. And that's 0 times infinity. Well, that's not helpful. So let me say what this is. This is another indeterminate form that ends up being 0 over 0, in fact. But I'm thinking that you don't like cotangent as much as I dislike it as well. So what I'm going to do is I'm going to rewrite that cotangent as 1 over tangent, because those are reciprocals. And now I'm a lot happier. By substitution, that becomes the opposite of 0 over, and tangent of 0 is 0. So that means it's eligible for L'Hopital's rule again. You can use L'Hopital's rule repeatedly as long as you're getting, by substitution, 0 over 0 or infinity over infinity. You can use L'Hopital's rule as many times as you need to, given that the conditions are met. So got to be real careful. You can't indiscriminately just start taking derivatives all over the place. You can only do this if it's 0 over 0 or infinity over infinity. All right, so the derivative of the opposite of x squared is negative 2x. And the derivative of tangent of x is secant squared x. So let's see what that gives us by substitution. Negative 2 times 0 is headed towards 0. And the secant of 0 is 1, and 1 squared is 1. And so that's actually a numerical value, 0. So the natural logarithm of y is 0. So that means that y is, by definition of logarithm, e to the 0, which is 1. And so therefore, the limit as x approaches 0 from the right side of sine of x to the x is 1. All right, so I'm going to stop this recording and start a new one because I'm at the bottom of the page. So move on to the next recording.